In this session, we're going to be moving beyond the procedural or imperative paradigm and look at object-oriented programming paradigm. Now, you've covered procedural in a lot of depth ever since you've been taught computer science, the use of procedures and functions. We know how it works, selection, iteration, so there's no point in covering that all over again. Hopefully, by the end of this session, the terminology associated with object-oriented programming, polymorphism, containment, which is also known as aggregation, getters, setters, instances, will be clear to you. You will develop an understanding of how to solve a problem by designing appropriate classes, and you'll be able to gain the ability to write code that demonstrates the use of object-oriented programming concepts. And we're going to put all of this together in the implementation of a binary tree, which is very important for paper 4, because chances are that you'll be asked to code a binary tree and traverse it to generate some output, and classes are one of the best ways to deal with it. Similarly, you could apply this to linked lists as well. So quite a jam-packed session, so let's begin. Okay, one of the key properties of object-oriented programming is polymorphism. But before we talk about polymorphism, you also need to know about inheritance. Now, inheritance works exactly like it would work in real life. You inherit something from your parents. So when we create an object inherits the methods that are defined for a class. So you set up a class, which is basically a template, and then you use inheritance to ensure that any objects that are created based on that template inherit the same properties and the same methods. Polymorphism, on the other hand, is the process when methods are redefined for derived classes. So, for example, you've inherited something from a parent class, but you are now redefining it to make it a bit different than the method that was in the parent class. In essence, you morph the original method to do something completely different. Now on screen you see an example of a parent class called shape. So in here we have a constructor which defines the area value and the perimeter value. We set those to 0. And then we have a definition for the area, a method. And this method simply prints the area out. In this case, it'll just print out 0. And similarly, we've got another method that prints the perimeter out. Now, we're going to use this class to generate a new class called rectangle, because rectangle is a shape. So shape becomes the parent class of a rectangle, and we simply do that by simply saying class rectangle and in brackets shape. That basically means use the shape class as a template for this one. Now the rectangle class will inherit all of the methods that are present in the shape class, but it can also have its own methods. So the new constructor that's been created for the rectangle class has a command at the top which says shape.init, and that means initialize the previous constructor and then add 2 extra attributes, which are the length and breadth. So you're inheriting the original perimeter and area values and adding length and breadth, which are unique to this particular constructor for the rectangle. And then similarly, if you look at the area definition, we can redefine it to use the length and breadth to calculate a new area and then print that area out. So the original area that was in the shape class has been morphed to a new definition in the child class. So both the original class and the derived class have a method called area, which is now going to produce different results. And that's an example of polymorphism. Another way to extend the constructor is to use the super brackets.init approach, where we can extend the parent class's constructor by adding extra attributes. And this is very useful when you're coding in Python. And I think there was an exam question in the past that asked you to extend the constructor by adding extra attributes. And this is the method that you would be using in code. So in this particular example on screen, the derived class rectangle uses the super.init method to inherit length and breadth from the parent class, or the superclass as it's called, and then defines the area and perimeter attributes. And these new attributes are only available to the derived class and not the parent class. So we have an example of inheritance, polymorphism, all in one place. Now sometimes you might not want to use multiple classes to do the same thing, because imagine you have a shape class, then a rectangle class, then a circle class, then a square class. You have too many classes. So in that particular case, we can use a concept called overloading, And this is when a method is defined more than once in the same class, so it can be used in different situations. Perhaps you don't want to have two classes, but you want to use the same class to deal with two situations at once. Overloading is managed by the use of parameters and a selection statement. So for that example on screen, we've got a class called greeting and we have a definition called hello, where there's a parameter that's imported, which is the name. And if the name is none, that means it hasn't been entered, we can use the selection to simply say, well, if the name is not none, that means somebody's entered a name, then print hello name. Otherwise, you just print hello because we don't know the name. So instead of creating two different classes to deal with a name being entered or not entered, we're just going to use the same class and parameters and a selection to get the same effect. Now we could achieve the same via polymorphism, but we'll need to code two separate classes, a superclass and a derived class, and that could be a lot lengthier. So when we're executing this, we create an object called myGreeting based on the greeting class. myGreeting.hello without a parameter will just simply print out hello. myGreeting.hello with a parameter, for example, Christopher, will print out hello Christopher. And that's an example of how we use overloading. Another concept is containment, and this is the process where one class can contain other classes. To me, this is slightly like inheritance, but the other way around. Inheritance basically means you have this root at the top, which can then generate all these objects. When you flip that structure, that's where you have containment. So the aeroplane class in this particular case contains the seat class, the fuselage, the wing, and the cockpit class. And it can use the methods of all these other classes, but those other classes can't use the aeroplane class's methods. So when deciding when to use containment or inheritance, which works the other way around, you need to look at how objects are related to each other in the real world. So when looking at shapes, think about this. A circle is a shape, so inheritance is used. When looking at a car contains seats, so containment is used. Now for our aeroplane example, if a plane has 10 crew members and 300 passengers, the class diagram would look like the one on the right. We've got two classes called crew and passenger. The crew has the first name, last name, and the role of the crew member, and it has show crew details method, which allows you to print out perhaps the crew's details. And similarly for the passenger, we've got the first name, last name, and the seat number, and show passenger details is a method that prints those out. Now flight, on the other hand, needs a flight ID, how many crew members it has, which in our case is going to be 10, and then an array of 10 crew members, which will be based on the crew class. The same goes for passenger. You will need an array of 300 based on the passenger class template. So the flight has some additional methods like add crew, add passenger, remove crew, remove passenger, which do not apply to the crew and passenger class. Now also pay attention to the arrows. The arrows will go upwards because the flight is containing the crew and the passenger. Whereas if you were using inheritance, the arrows will go downwards because you are inheriting the properties from a particular class. Okay, a little task for you. Try to draw a class diagram for a subject in a school which has 50 lessons, 3 exams, and the final mark is the average of the 3 exams. Now on screen you see some examples of class diagrams. You've got the basic class diagram on the right hand side, which is pretty simple. And then you've got an extended class diagram with the attributes and the methods. Feel free to invent your own methods, and the attributes need to be in line with what the context suggests. Think about it, pause the video, and have a go at completing this particular task. In addition to the concepts that we discussed a moment ago, you also need to be aware of the object methods. And chances are that if you have been experimenting with classes and objects, these methods you might have been using them, but you might not be familiar with the terminology. So the basic methods that can be used in object-oriented programming are constructors, and these are used to initialize an object, getters, which are used to get a value of a property in an object, setters, which are used to change the value in an object, and destructors, which are used to destroy an object. Say for example, you've got a car class and you created car 1 and you want to delete car 1. That's where the destructor method comes into play. So we're going to be looking at examples of these in code, and chances are that you're probably already using them, but you're not actually calling them using these terms. So let's start with the constructor method. It's used to initialize an object, and this is done when a new instance is declared. When an object is initialized, memory is actually allocated to it. So normally you would probably use the def underscores init underscores bracket and whatever parameters that you're passing to it. So self refers to itself. So whenever we create a new object based on this initialization, self refers to that object. So it could be car1, car2, car3, whatever. The name and the staff number are then the parameters or the attributes associated with that particular instance. So this part is called the constructor, and you have to define it for a class to actually be operational. When we're constructing an object, that means we're creating a name for it. So in this case, we're using my staff, and we're simply saying use the employee class and then pass these two arguments to it. So in this case, the name and the staff number are used to create an object in memory based on the employee class. A setter is used to control changes to a variable in an object, and private variables can only be changed by the setters defined in the class. This makes the program more robust and secure. So if you think back to our employee class, we already created an object, my staff, which has a name and a staff number. What if we wanted to change that name? Now, we can't do that using the initial constructor method because you're going to overwrite all the other information, which is just not very efficient. So in this case, we create a setter definition or a setter method, and we're going to call it setName, which is going to use a parameter n and then use that parameter to change just the name part. So once I've set this up, all I need to do is simply say my staff dot set name brackets and type a new name in, and that will change the name of my staff. It will update it. Will set it. Now getter, on the other hand, simply gets the value of a property in an object. So it's like read and bring it back. Set is more like writing it. And again, we create a new definition. In this case, we call it get hours worked, and then we're simply going to return the hours worked back to the main program. That's how simple it is. Very easy to use a getter. Now, please make sure that you are remembering these key terms, because exam questions will often refer to these. Create a setter, create a getter. All you're simply doing is writing a property value or reading a property value and returning it to the main program. And finally, destructors are used to destroy or delete an object, and when an object is destroyed, the memory is released to be reused by something else. Some programming languages can do this automatically if an object is not being used. In others, you have to specify it. So in Python, we just create a definition called del. We don't even need to write any more code for that. So def del self basically means when this del is called, delete any object that it refers to. So if we create an object called my circle, then we want to remove it, we can simply say del my circle, and that object is destroyed. It's very easy to use in Python. Now, it's all well and good knowing all of these terminology, but the purpose of coding is to actually create code. Now we're going to look at creating binary trees using classes and objects. Of course, you can create these using arrays and all sorts of other mechanisms. However, the best way, the quickest and most efficient way is using object-oriented programming. So how does it work? Well, we can use objects for the tree and node. Constructors are used for adding a new node to the tree. Containment principles are used because the tree actually contains nodes. We can create functions to search the binary tree for an item and procedures to insert a new item in the binary tree as well. And recursion can also be utilized. So let's see how all of this works. So for the tree and node, we can create a class called node, and the constructor will contain the item that we're trying to put in. That's the data value. We also need to ensure that we have the left pointer and the right pointer, and these are set to none, which is Python's version of the null pointer. You could obviously change it to -1 as well if you wanted to work around with the numerical form. That's up to you. And the item, self.item, equals the item parameter that we're passing to it. So once we set this class up, we can set the root of the tree as an instant of node. So tree is equal to node 27. That means that the first node is going to be 27 and the left and right pointers are going to be none. So how do we add another integer to the tree? Well, we can use a recursive procedure because obviously you need to keep checking the pointers until you find the right place. So we're going to create a method called insert, which is going to take that new item value that we want to insert. And if self.item basically means if the node exists. If it doesn't exist, then don't do any of this because you need to insert this in the first position. But if there is an item already, that means we already have 27 as the root node, we then look at the next one. We then say, well, if the new item is less than the item in the root node, then we check if the self.left is set to none, that means if the left pointer is none, then we simply say that self.left is now going to be node item. So we're going to go back to node and use that method to insert this item to the left of 27. Otherwise, we then go self.left.insert and we use recursion to check the pointer of the item on the left of the root node, and we continue doing that until we find the none, so we can put the item using node in there. Otherwise, we check if it's greater, then we go to the right and we repeat the same strategy. So do pause the video and study this code in depth, try to code it and see how it works. So what if you want to search for an item and see if it exists in the binary tree? We can use a simple function here, and this particular function returns whether the item exists or none if it's not found. So while self.item is not equal to the item, check if the item is less than the root node, and then the self.item is equal to self.left, else self.item is equal to self.right, and keep doing it. If self.item is none, then return none, otherwise return the item if it's matched. Time for you to go and program a binary tree in Python, which sets the root to 27 and then adds integers 19, 36, 42, and 16 to it. The final tree should be output. As a challenge, try to implement a pre-order, which is root left right, and a post order, which is left right root traversal of the tree as well. Now, if you're stuck and you're not sure how to do this, obviously I'll share the code with you so you can study that particular code and then try to see if you can implement it on your own. So on screen, you'll see a possible implementation of this type of structure. Check whether you can identify where classes are used, where the objects or instances are created, where the methods are, where the getters are, any particular procedures, and where recursion is being used. Pause the video and you could type this up and check whether it works. But that's all from me for today. Hopefully you understand what is meant by polymorphism and what's meant by overloading and containment. You understand what the four main types of object methods are, and you can explain what each object method is used for. In addition to this, you should know how to code binary trees and linked lists using classes. So do experiment with that. Make sure that you're also familiar with the basic terms, such as what a class or an object is, what's meant by inheritance, what's meant by encapsulation, and so forth. That's all from me for today. If you do have any questions, please do get back to me. Otherwise, I'll see you in the next one.